I'm Steve Tazari, Director of the Weed Center, and welcome to our event for today. Thanks for registering for this event. We've changed our logistics here a little bit, which allows us to spread our reach a little more widely with more broader announcements in other places. And I see some names here that I hadn't seen before, and that's really exciting. So I'm happy to welcome our speaker today, Professor Sophia E from the Department of Chemistry. Sophia received her PhD in chemistry from the University of California at Santa Barbara, a very nice place, and did a postdoc at the prestigious Lawrence Livermore Laboratory. She joined the WashU faculty and has risen through the ranks in the Department of Chemistry, is now Professor of Chemistry. She is an award-winning teacher, receiving special recognition for excellence in mentoring from the Washington University Graduate Student Senate. Sophia has widely published research that addresses the properties of semiconductors and how lasers excite and spit electrons. But of particular relevance to our discussion today, Sophia has studied processes for capturing carbon dioxide from the atmosphere. I've had the pleasure of working with Sophia for a number of years on the Arts and Sciences Academic Planning Committee, and many of us in the Wiedenbaum Center really enjoyed her presentation sometime last year at one of our policy lunches on helium and what helium does in her lab and the price of helium. Maybe she can update us if we have a minute. Sophia is a really fine scholar and a terrific colleague, and I'm really looking forward to her talk today. We're going to do something a little bit different. Sophia has done a very nice TED Talk on this topic to just kind of introduce the issues here. So we're going to play her 8-minute TED Talk right now for everyone. And then she'll join us to elaborate and go into a little bit more detail. So again, thanks, Sophia. And Alana, go ahead and start the TED Talk.
I am a chemistry professor, but I'm also a mom. My daughter, at an early age, became concerned with the environment. She was hearing about polar bears dying off, melting ice caps. She and her friends decided to form a Save the Earth Club. At 6 years old, in the first grade. Over the years, I've seen them become worried about the world that they will inherit. I see that concern in my daughter, and I feel that same concern in all of us. Climate change is a problem. We see changes in our weather. We hear about rising sea levels, whole cities, communities, even countries going underwater. There are large forest fires, crops that fail. This sounds dire. It is dire. What we've come to know is that high levels of CO2 in our atmosphere are responsible for these things, and they continue to increase with no foreseeable change, no decrease. But what I've come to understand through my own research and through hearing about the work of others is that there's reasons for hope. We can combat these rising levels of CO2, and we have reasons to be optimistic because we have done it before. As a nation, as a globe, we have tackled big problems in the environment. We used science and engineering to solve an atmospheric pollution problem. Some of you here will remember the acid rain of the 1970s, the brown forests of Europe, the marble statues whose features began to melt as acid disintegrated them. The world saw this and recognized that they needed to do something about the components of acid rain. These are chemical pollutants that we found at high levels. So treaties were formed, agreements were made. We began to use a new technology. It used a material that had been discovered in the 1950s, 20 years earlier, by a French scientist named Eugene Houdry. His materials sat on the shelf for decades until it was recognized that something was needed to clean up these pollutants. They began using it in smokestacks and chimneys of power plants and factories, and those scrubbing boxes removed those components, those pollutants that were responsible for acid rain. But I know many of us think, wait a minute, smog and things come from cars. What would we do about the millions of cars and the smog that they produce? It would simply be a problem that was too difficult, too expensive, too impossible. Except it wasn't any of these. Today, every one of us has one of these scrubbing devices on our cars. It's called a catalytic converter, and it uses those same materials that Hodry developed for us. And so now, as we drive around town, we're cleaning up our exhaust as we go. So imagine, what if we could do the same for CO2? What if we could capture it out of smokestacks and chimneys? That's called carbon capture. And there are new materials that are like sponges for CO2. It traps the molecules and holds them tightly, remarkably well, allowing other gases to pass through. And when society is ready, we'll have these materials ready to deploy to solve the problems of high CO2 levels that lead to climate instability and a warming planet. These carbon CO2 materials are remarkable. In the space of only a thimbleful of this powder, it has as much surface area as 3 football fields. These materials have small pockets and tunnels and tortuous paths that hold the CO2 inside. And with so much real estate, well, a small amount of powder can trap a lot of gas. There are thousands of scientists and engineers trying to develop these new materials right now because we believe that this will help solve our climate change problem. Just as one scientist might use the equivalent of building block like Legos, somebody else is using something like Tinker Toys, and still somebody else like Lincoln Logs. With so many different people working with so many different building blocks, incredible discoveries can be made. So it might be easy to imagine capturing CO2 from smokestacks and chimneys, but what about the high levels of CO2 in the air around us? Well, it turns out there are several places worldwide that are attempting this at pilot scale. It's called direct air capture. And in one site in Zurich, Switzerland, they're using industrial washing machine-sized units filled with these special sponges for CO2. And it's capturing the gas molecules from the air. Imagine a solar farm with hundreds, maybe thousands of solar panels capturing sunlight and turning it into electricity. Well, we can imagine a CO2 farm doing the same, capturing CO2 and sequestering it. Now imagine for a moment, you have all this CO2 you've captured, what do you do with it? Well, in one project, a team is trying to turn it into artificial building materials in research funded by Bill Gates. In another team, they're trying to convert CO2 to a new chemical by adding just 1 atom of oxygen. Well, we chemists call that carbonate. You call it chalk. And the startup company that makes it calls it artificial coral that they hope to use to replenish coral reefs. Oh, and those guys in Switzerland, they recycle the CO2 that they capture. They squeeze it out from those machines, releasing the CO2 gas, and they send it off to a bottling plant to carbonate soda. So the next time you hear a dire headline, maybe your kids start a club, or your neighbors start to fret about climate change. Now you know there's not only hope, there are scientific solutions. And today, when people ask my daughter about climate change, she can share her concerns and also her hopes. She'll hold up a thimble and tell you how much CO2 it can hold. 3 football fields. We just need to get started. Oh, thank you. Wow. Thank you.
Well, thank you so much, first of all, for the introduction, Steve, and also Elena for indulging me and allowing me to play that video. The TED Talk was a really exciting time to bring some of these messages to that audience. So thanks for indulging me on this part. I'm going to take a little bit of a deeper dive, telling you about some of the technical details there, but not going too deep technically. What my TED Talk referred to is the fact that we now are experiencing the effects of climate change. And we see this in things like, forest fires and high levels of smog, floods, melting glaciers. None of this is surprising to us these days because it's become more and more common experientially to us all. And of course, connecting this back to CO2 itself. So we see these evidence of climate change, and we experience this directly. And then as scientists, we go and we look for data, and this is a plot here showing CO2 in parts per million, and you see an axis along this Y direction here, numbers that of course increase up to around 400 and higher, and these are in units of parts per million. Along this x-axis is the decade, what year these measurements were taken, and these are measurements of the level of CO2 in the atmosphere. And what's uncontrovertible about this evidence is that CO2 is increasing over time. And so then for a long time, there's been a question of whether there's a causal relationship between rising CO2 and temperature. And today, nearly all scientists agree that these two are in a causal relationship. So CO2 continues to be a problem that we'd like to solve in some fashion. In addition, some publications like The Guardian for a long time were publishing on just their web app a simple sort of CO2 census that you can pick up, as you see over here, where it was listing, for example, a date and what the ppm levels were in the atmosphere, but also what it looked like 10 years ago. And again, reminding us what is thought to be a safe level, or what the pre-industrial level was at 280 ppm. But again, just like the TED Talk, these are very dire experiences, dire predictions about things. And what we find is that I want to inform you that there's hope, because there are these scientific directions that we are taking to address CO2 in the atmosphere. Getting back to that example of Hodri, I just want to go on a little bit of a deeper dive there. So Hodri is the one who developed the materials for the catalytic converter. And it's only to make the point that, again, those were developed in the 1950s. But at that point, what these are is they're like ceramics. They're almost like, if you can imagine, a piece of stoneware that you might have in your kitchen. And the surfaces are kind of roughened up and decorated with atoms. And those atoms do some special chemistry that served to reduce sulfur oxides and nitrogen oxides, the components of smog. And yet those materials were sitting there really not doing anything until roughly the 1970s. And in part, it was stimulated by legislation. And if you think about a catalytic converter, it's a can-like object that rides on many of our cars. And it turns out there are very similar types of structures in power plants. And they're this sort of porous construction. You see these millimeter pathways where gas can pass down this structure and do some chemistry along the way. But if you look back to what the newspapers were saying, the press at that time, it had just a mixed reception. And so I'll just highlight in yellow some of the comments that were made. For example, it was everything from it's a tremendous achievement according to Chrysler's leadership, but in addition, they were also saying at the same time, this is the dumbest thing that ever happened to the automobile, according to one of the Chrysler vice presidents. And the comments were things like, it highlighted, and there's a lot of text here, so I won't read all of it, but it highlighted things like there would be added cost, of course, by using such catalytic converters. In addition, there were science and engineering folks even back then who didn't see how General Motors' approach could work. They said it was going to be complicated. It will hardly ever work, and it'll be useless within a year. And yet with all of that criticism in the early days, and this is roughly in the 1970 to 75 timeframe, yet today we see it widely deployed. Now let's look at that in terms of CO2 capture. So CO2 is our gas that we're addressing today, which was the acid rain of the 1970s. And what I want to tell you about is touch a little bit on new materials, and just to give you a framework for thinking about this problem. So I'll just highlight that here at Washington University, at Washington University, there are a number of people who are collaborators of mine, including Dan Jamar over in engineering. Outside at Georgia Tech, there are two collaborators who have contributed significantly to this talk, Chris Jones and Krista Walton. And I worked with Sandia National Labs extensively. But not only my work, there are a whole host of other faculty members looking at different aspects of CO2, both on the energy generation side, which reduces the amount of CO2 produced, and also what we can do to clean it up, almost like imagine as an environmental remediation type of effect. And here, my work is funded by 2 DOE centers and also the National Science Foundation. So there's a lot of interest. So again, thinking about rising CO2, what can we do? Because remember, this is the CO2 that's in the air around us at roughly 415 parts per million today. So thinking about those new materials and highlighting things like that catalytic converter made out of ceramics in the past. So again, what I said in the TED Talk is a thimbleful, roughly, of some of these new materials. It does have the surface area of 3 football fields, meaning that for every single blade of grass, you could imagine sticking a piece of CO2 onto each one of those. And so that little thimble will be able to capture a lot of CO2 itself. And so this is a very, very high surface area material, but it's also highly tailored in ways that are possible because of chemistry that's emerged in the last couple of decades. And so showing this kind of molecular diagram, we chemists and a lot of engineers look at these and it means something to us. I know these structures maybe mean less, but each one of those little balls represents an atom, and the different colors represent different types of atoms. And so what you're seeing here is a schematic where imagine CO2 reacts selectively with some of those atoms that are there that are green or red, and they do other kinds of chemistry, and we can tune that because we have the tools to do so. So just to give you a flavor for this, it turns out that we already touch upon highly porous materials in our everyday lives. You know, activated carbon is something known to many of you. If you have a Brita water filter in your house or you have one under your sink, this is a highly porous substance that's used to remove pollutants and something that you already know from everyday life. There are also zeolites. This is another highly tailored porous structure. It turns out that zeolites are in many laundry detergents. And what these do is they remove oils and scents, for example, that we consider dirt or some kind of, some kind of thing that we want to remove as an element. But now the more tailored metal organic frameworks, those are the ones that have this football field kind of surface area. You see they're very, very high in surface area. I give the units here as greater than 6,000 square meters per gram. Those are those football field dimensions. And so these tailored materials are all different classes of porous things. I'm going to show some schematics here, just cartoon-like images. And so one way to think of these is we can classify activated carbon as something on a micron scale. A micron is a dimension that's on the order of, let's say, human hair types of scales. So it turns out that activated carbon types of porosity goes all the way from human hair to sort of bacteria sized, if you will. But if you go just to the next class over, and we're going to talk a little bit more about the one next door, those zeolites. It turns out those zeolites are a large molecule scale. You know, it's got to trap big, large, oily molecules, and those are large relative to CO2, which is a tiny little compact kind of species. But it turns out that zeolites are great host materials where we can decorate their surfaces, kind of like Hodry did with the catalytic converter. And then last but not least, the metal organic frameworks are a new class also, in part because those are tailor-made. Each individual gray group that I show here in the schematic and each individual colored sphere can be tailored by a whole bunch of things within the periodic table to do different kinds of chemistry. So thinking about this sort of globally, remember what we had in the 1970s over here on the right. We have millimeter scale catalytic converters with things that we can see by eye, all the way down to this small molecule atomic scale, where we're looking at these CO2 molecules are shown here, again, for schematic purposes, interacting with the walls. And these high surface area materials have so many adsorbent sites, these are seen as a game changer for the CO2 world. Okay, so let me talk for a moment about this and putting these into context. So there's a terrific National Academies report that links will be provided so that you can go to some of these references. But if we think about CO2, there are two big blocks, for example. We can reduce those CO2 sources, and we said reduce those carbon sources. That would be CO2 or even methane, both of which are greenhouse gases. And that we can achieve through energy efficiency, again, using zero carbon fuel sources, meaning non-hydrocarbon based. And that's in the area of wind and solar and so forth. We can also, on the right-hand side, enhance these carbon sinks. In other words, find ways to take the carbon out. And there's a whole bulleted list here of possible options. And the one that I'm going to talk about today is actually direct air capture, the one underlined in red, because these are the ones where these special materials will be deployed especially. I'll just pause for a moment and say that in this talk, there are several different abbreviations that are commonly used, and I switch back and forth between them. Here, for example, is a plot out of a IPCC report. And here we're talking about greenhouse gas emissions, that's GHGs. And so sometimes we use the unit of little t for tons of CO2 and big T, capital T, tons of CO2. And we will interchange between a gigaton, which is a billion tons, and the word billion tons. And so forgive me for some inconsistencies there, but hopefully the message will come through. So out of the IPCC report, the Intergovernmental Panel on Climate Change, they have excellent resources to start to understand, where technologies are headed and what the potential is. So here on this graph is greenhouse gas emissions along the y-axis, along the x-axis is decade by decade. And notice that we're looking into the future. The Paris Agreement goals are to keep our global temperatures below a rise of 2 degrees Celsius. And that's shown by this red line in this graph. And so this graphic has a lot going on, and it depends on certain climate models, of course, but it's simply to say and encaptures in one graphic that you can do some of our shaving of that peak, if you will, by using these conventional abatement technologies, meaning going to other kinds of fuels. In addition, we can think about better ways to, when we create CO2, to do it more efficiently. That's this brown block of emitting technologies. Can we switch from coal to, for example, oil or natural gas to be less emitting of CO2 for our energy sources? But by far the one that holds the most excitement for me and others is this idea of carbon removal. We have 400 ppm in the air around us. We want to get it to at least 350 ppm in order to be in a safer range. And ideally, that would require us removing some of that CO2, of course. So just let me give you, I don't like slides with lots of text and numbers, but let me highlight a few. And again, this would be there for your reference later. So the US emissions roughly are estimated to be about 5.1 billion tons of CO2 per year. So that's just what we are producing that we would like to clean up for our own country. Global emissions are estimated, depending on who you're speaking to, at about 32 to 40 gigatons per year, 32 to 40 billion tons. And the CO2 in the atmosphere, just to remind you, is 400 parts per million. By the way, I heard a great analogy about this on Nova recently. A scientist there said, if you put 10,000 ping pong balls in a box and you color 4 of them black, those are your 4 CO2 molecules that you're trying to find and filter out of those other 10,000. And so that's a great mnemonic to give you a sense. So while they are very dilute and we don't sense them directly, even those 4 have that amount of effect on heating the planet. Clearly, it's something we need to address. And then lastly, Scientific American produced this nice metric that between 1751, which is some argue is the start of the Industrial Revolution, and 1987, in those 136 years, there were roughly 737 billion tons of CO2 produced. And just in 27 years, we've essentially equaled that amount between 1987 and 2014. So it's clearly speeding up as we use CO2 for combustion, for transportation, for a number of different things, and as the population grows on the planet. So these anthropogenic sources of CO2 definitely need to be addressed. All right. So the key messages then are going to be that we now need to deploy what are called negative emissions technologies to prevent this warming. And this is using an assumption that we will continue to use fossil energy for decades. And in some fashion, even if we reduce fossil energy use, it will still be necessary to help with the warming that's going on now. And in general, most scalable negative emissions technologies employ these kinds of CO2 sorbents. And so that can be classified into direct air capture. And also there's a general term called carbon capture and sequestration, CCS, that is actively studied by a number of people on this campus. People in earth and planetary sciences, in energy, environmental, and chemical engineering, and there are very active research programs that are looking into both areas. So let me just give you a schematic so that you have some idea of how this works. So in general, you have CO2 and then a non-CO2 gas. Most of the time, this is nitrogen, but it may have some other things mixed in like water and so forth. And in the presence of an adsorbent, usually at slightly elevated temperatures, like we find in those smokestacks, there will be a tendency for CO2 to adsorb, luckily, onto the surface of those filtering materials. Eventually, the other gases will pass through, and there is an idealized 90% removal. So a little CO2 will probably break through. And nevertheless, most of the CO2, though, has been stuck inside the adsorbent. When we're done with that process, we then have things we can do to release it, usually by elevating the temperature even further. And that's really, that's really convenient at a power plant where you may have excess waste heat. And engineers do this on a daily basis. They think of ways to use waste heat, for example, for these other processes. And then on releasing it, that CO2 can be sequestered, which is an entirely different talk. And we study that in my lab also. But you can also convert it. And in the part of the TED talk that got cut off, the CO2 coming off the direct air capture plant that I showed is actually being shunted over to be used in a greenhouse for growing some vegetables, but also for carbonating sodas. And there are other product lines that chemical engineers and chemists are designing to convert that CO2 even into other feedstock chemicals, rather than wasting it and throwing it away. So that gives you sort of a sense of what this looks like. So there's two sides of the equation. One is an adsorption process, one is the desorption, and both have to be able to be performed at low energy cost in order for this to be a cost-effective scenario. Steve was kind enough to indulge me and let me show just a tiny amount of chemistry. I promise we won't do too much more, but in the language of chemistry, I'd like to show you a little bit about this. One of the technologies that this works so well is employing little nitrogen-bearing substances called amines, A-M-I-N-E, amines. So amines, and in the calligraphy of chemistry, we draw these stick figures to indicate certain kinds of chemical structures. I'm just going to say that this amine that's shown here in this small reaction can be tethered onto a surface. We can stick it onto something by the other end. But what's lovely about this chemical is that CO2, which itself is relatively unreactive, fortunately for us, tends to get up close and personal with that nitrogen. It transfers a bit of charge, and in doing so, it creates a new chemical. What you see below in the second reaction is that nitrogen now has a carbon with two oxygens attached to it. And this form now is what is present on the adsorbent in some cases. And so these amines are part of that flexibility that we have in chemistry of trying to link things together and look at a huge amount of variability in what the rest, for example, of this tether looks like, what else is bound to the nitrogen, and a whole bunch of different tailorable properties. And for those of you who are more deep in the weeds on this, I give a simple statement that we and others study, for example, primary, secondary, and even tertiary amines, and also sterically hindered amines in order to look at the reversibility of that process. And that's it for the chemistry part. So I'll leave it low. Okay, In addition, I showed a zeolite earlier, and this is a zeolite type of host. And I schematically show that blue wall here of what that zeolite looks like. And remember, that was for capturing big molecules. Well, some of those nitrogen-bearing tethers in these stick figures can be stuck to the walls of that zeolite, and in some cases can just kind of sit inside there waiting for CO2 to come by. By the way, this is called a polymer here in the top figure, and down here, these are just tethered molecules. But again, the almost infinite flexibility of chemistry allows us to do this. And every time you see a nitrogen, there is the possibility here of binding a CO2 to it. And so when you can cram a lot of nitrogen into these high surface area materials, this is what gives us hope for these to be materials that can be used to do this direct air capture. Okay. Breaking it down, then, there are two sides also of where we want to get CO2. CO2 can come out of a flue stack, that's shown in gray here. And to get you to think about it, this has fairly high concentrations of CO2. 5 to 15% of the stuff flowing out of that chimney is CO2, so it's a high concentration source. There's also usually high temperature available, which is great, but it's got a problem. Down here under contaminants, it's got high levels of, remember, SOx and NOx? Those were Hodry's special materials, special gases that he was addressing. It turns out that those can also interact with some of these catalysts. And so that has to be addressed at times. So we think of this as a purification type of step. Let me give you an analogy. It's kind of like your kitchen fan that you might use over a stove. You've got oil and smoke flowing through it, and you just want to have all of those oily, smelly components taken out. And so it's flown at fast rate over something that would absorb those kinds of things. In this blue box is the other side, the direct air capture side, meaning that in the air, well, we have 400 ppm around us at all times, even right now. Here, though, we'd have to be able to do air capture at lower temperature, and maybe it's going to cost me some energy to squeeze that CO2 out. So I have to design a material that's very different for the air capture case. But on the good side, there's low levels of contaminants, well, because we have those catalytic converters already going. And so in the end, these are two very different kinds of problems. We can think of that as an extraction sort of problem. It's almost, again, like your water filter. Your Brita water filter is removing small amounts of contaminants out of that water stream as it flows through, and it binds things until, again, that you want to recycle that filter, reuse it. So this is just a slide to say, here in one nutshell is a snapshot to give you a sense that there are so many different materials. I have only talked about a couple of them. And this graphic in the middle, taken out of a SusChem article, and a bit dated one at that, it shows all sorts of different capacity here on this y-axis for CO2 absorption, and what the operating temperatures are. And it's simply, the plot serves to say, there are so many different materials, and people are fine-tuning them to find the ideal material for the two applications that I showed a moment ago in blue and gray. So what many of you might be thinking of is, why aren't we doing this? I mean, this just makes a lot of sense. So unfortunately, as this has been studied for a number of years, there have been some case studies that have come out in the literature that put a damper on all of this exciting research. So back in 2011, a PNAS report from House and coworkers estimated the cost of direct air capture to be $1,000 a ton of CO2. And when you're talking about 5 gigatons, 5 billion tons, this is a huge amount of money. And of course, it just doesn't seem feasible. Recently, McDowell and Energy and Environmental Sciences also had a different type of study in 2018 that was published, even at 10,000 a ton. I mean, these numbers are so high that it's almost enough to keep us out of the research game, because it just doesn't seem like it'll ever be tractable. And in 2011, there was an APS report that studied these processes in detail, and I show this reference here. Well, these are a little bit unfortunate because some of the case studies may have had certain assumptions baked into them having to do with how the CO2 was captured and how it was sequestered. And so more modern versions of these initial reports that almost certainly damaged the field back in 2011. And so newer approaches have been taken. We talk about those. So I'll just say, this third point for these key messages is that recent R&D suggests that direct air capture technologies have the room to get down to the $100 per ton CO2 level. That is actually the target that many groups are seeking to get to. And remember, we just saw $10,000, we saw $1,000 per ton. So at $100 per ton, it's still expensive, but at least that gets into a realm of feasibility. So let me tell you about a couple of them. In the TED Talk, you already saw this company, Kleinworks in Switzerland. So right now, their current operating costs are $400 for one of their plants, $600 per ton for another of their plants. And these units are shown for scale so that you can kind of see next to a van that these are modular and these employ. In addition, there's another US-based plant over in Menlo Park, California, near Stanford, called Global Thermostat. And they don't make their costs available yet, at least for analysis, but they're also using slightly different technology, but also working on the cyclability and again, the direct air capture for these types of materials in a completely different envisioning of how this material would be deployed. And so a slightly more modern air capture evaluation was just done a couple of years ago by the National Academies. Again, they have different cost estimates that will be, I think, useful to those who are evaluating the costs of direct air capture, again, with $600 and $1,000 per ton estimates. But again, with new materials, many people believe that this could drop even further. But just to highlight the last point, low cost direct air capture isn't a sure thing. And for certain, new materials, new processes are going to be needed. So many of this, oh, there's a misspelling on the slide, but okay, it's our moonshot of the 21st century. So basically carbon capture as a field, whether you're talking about direct air, flue gas, or even sequestration, carbon capture and sequestration really requires traditional chemistry and chemical engineering skills. There's a whole adsorbent and solvent design to figure out these processes. There's also the reactor component, how we take and do lots of mass transport, heat transport, the concerns that normally concern our chemical engineering colleagues. And so if we think about this, in the 1950s, there was Sputnik and the space race. In the 1970s to 90s, think about the microelectronics age, the emergence of the internet, whether or not you think that's a good thing. And then the information age here in the early 2000s. And so a number of people believe that the 2020s and onwards, that's going to be our energy and carbon management age. It's going to be the defining problem of this generation. So Kleinworks, this photo is one that I like because they're the ones that are squeezing that CO2 out and sending it off to a Coca-Cola bottling plant. And they also have greenhouses in the background. And so these guys had great vision, as do others who are trying this out at pilot scale. And so these folks give us hope that we can actually do this. And so remember that even as we see all this climate change around us, there are many scientists, as I said before, who are doing this and who put their heart into this work because we believe there's a solution. But also, I just want to remind you that I'm not here just to represent my own research, which Washington University has so generously helped me start up and continue all these years on this topic that's near and dear to my heart. But also I've been sent here by the Save the Earth Club to talk to you all about it. So remember, these are the folks that we're really doing this for. And with that, I thank you for your attention.